All right, hello there, calculus folks. This video is the lesson on the derivative of general exponential functions. And if you don't have this sitting in front of you, you should probably pause the video, stop the video, go print off a copy of this so you can sort of fill in as we go along, make your life easier. You also pause the video and try the warm-up, and then when you're ready, I'm going to go through it real quick. So go ahead and try it on your own. But here we go. This one way we thought of solving this is to just change the form. This is in exponential notation or exponential form, and I could, if I wanted to, rewrite that as, well, the answer is log, it's base 2 of the power, and we realized last semester that a logarithm is just the exponent, and so this would be the same way to rewrite it, but log form. And then hopefully we can remember how to put this into our calculator. Some calculators these days actually do logs of various bases, but how I actually think about it is I think of the operation of taking the log of both sides. So, and I used log base 10 because log base 10 is a button on our calculator. Of course, we know now there's another log base that we could choose, but log base 10 works fine. And then the x comes down in front, and hopefully we remembered some of this when we did our preview to chapter 5. And this expression is the same as this, and actually that's what you would have learned in advanced functions as the change of base formula. Well, this is the same thing, right? Except I don't really want to take log base 10 because this is base e, and log base e, which the natural log is the ln, is a button on our calculator. So I could take the ln of both sides instead. Right? And this is a function composed with its inverse. These kind of cancel each other out. And that's it. There's the answer. And so that's kind of nice. I've got a new base that I can use in solving exponential equations, base e, or the natural base. What's the second one about? Well, the second one here is essentially going to lead us to the derivatives that we want to be able to take. It says write 2 to the exponent x as a power base e. So essentially what we want to do is solve this exponential equation, right? Where 2 to the x is the same as some power base e. And notice that if I'm clever about this, really all I'm looking for is a value of k that makes this true, right? Because the x's, I could take the xth root of both sides if I wanted to, and then I'm left with just this little equation where I'd like to find out what k is, right? Well, how do I solve what k is? Well, I take the ln of both sides, the natural logarithm of both sides, just like I did up here. This is almost the same equation, isn't it? And then this side becomes k, and the left side is the ln of 2. So therefore, 2 is e to the exponent ln 2. That's what k is. Well, that makes sense because that's a function composed with its inverse. Exponential function base e composed with logarithmic function base e, and those would cancel. 2 equals 2. This makes sense. This will come in handy shortly. Essentially what we're doing, and what we saw yesterday, is we know that the derivative of this function, you have to write this down, the derivative of that function is just the exponential function. And unfortunately, for other bases, base 2, base 5, base b is what we're after today, it's just not true. But that it's the same thing, and it's not base e, but it's pretty close, as we'll see. I've got a graphing calculator warmed up here. And what this does, and it's pretty cool, I can type in any function that I want, and I put the exponential function base e in there, and then in y2, it will take the derivative. So it goes along at each point, calculates the slope of the tangent, and then plots this new function, the derivative. And as we would expect, what happens here? Well, they're on top of each other, right? It wasn't very nice looking because it didn't graph it slowly. I had set it up before, but there's the original exponential function, and here comes its derivative in bold. It's got a thick, bold line here. And look, it's right on top of it. And we found that out in several ways this week. The question is, if I change this base, what happens to the derivative? So for instance, if I do 2 to the exponent x, not 2 to the exponent 2, that won't be very interesting, 2 to the exponent x, and take the derivative, what's the answer? There's the original exponential function, base 2, and here comes the derivative in bold, lumbering along here. You see it's a little bit lower. The exponential function base e was right on top of it, but it's a little bit lower. Almost looks like it's been squished down or horizontally stretched. This has been horizontally stretched this way, perhaps. And other bases will give me different answers, right? So if I go base 3, for instance, what's going to happen there? Well, there's the original exponential function base 3, and here comes its derivative. And the derivative is some sort of exponential function. Almost looks like it's bang on top of it, but that's really because 3 is so close to e. But if we change this to some other base, like 8, we'll see there's the original exponential function base 8, and here comes its derivative. It's an exponential function that looks like it's been sort of horizontally squished. It's been pinched in. It's still an exponential function, that derivative, but it's not the exact same graph. It's been transformed in some way, and our goal is to find out how, and that's what the next slide's all about. There's the title. Get rid of you. Get rid of you. And here's exactly what I was talking about. There's the 2 to the exponent x, and there's the derivative. It looks like an exponential function that's been compressed. And this one has been horizontally squished, it looks like, right? And so that is, it looks like this is the case, right? Where we've got some sort of vertical, in this case, vertical multiplier, but we don't know what this is. We need to find that, and it looks like it changes maybe from a fraction to a non-fraction depending on the value of b, depending on what the base is. And that's what we're up to today. Okay, here's what we're up to, right? We want to take the derivative of any old exponential function, even though we don't know what its base is. Well, how do we do that? Well, what we're going to do is we're going to use the fact that we learned in the warm-up. Any old exponential function can be written as e to the exponent kx. Well, what's k? You could probably guess. K is just the ln of the base b. And again, I'll prove that to you real quick, right? The x's kind of cancel out. Take the ln of both sides, and I've got it straight off here, right? This k is just the ln of the other base b. And so, well, what does that mean? Well, that means I could write b to the x as e ln bx. Well, why would I want to do that? I'd want to do that because I can take the derivative of the base e one, right? So if I want to differentiate that, why don't I write it as the one that I know? Take the derivative, right? This thing here is b to the exponent x. These are the same thing, right? We just showed that over there. And now I take the derivative. The derivative of e to the whatever is e to the whatever. But remember, we got to use the chain rule, right? So what's the derivative of the inside part here? Let me get a different color, just so that, what's the derivative of the inside part? Well, the derivative of the inside part is just ln b, right? If it was 4x, the derivative would be 4, right? But it's not. It's ln bx, so the derivative of that is ln b. This is the derivative of the baby, right? This is a chain rule function. Well, hang on here. This mess is actually just b to the exponent x, and then ln b. So there's our stretch factor that we were looking for in these diagrams. That stretch factor was ln of 2. And in this one, this stretch factor was the ln of 5. And we wouldn't have guessed that maybe, but there it is. Here's a box-worthy statement. Put this on your big page of derivative rules that you're developing. Ln of the base. And so now we're just practicing basically same lesson as yesterday. Take some derivatives, solve some problems, and that sort of thing. How am I doing for time? I don't like these videos to be much more than 10 minutes. And then yeah, I'll stop this and then finish off the rest of the lesson in the second part of the video. Okay.